Okay, let's get started. All right, so the quiz is due Tuesday, right? And when I don't put a time of day on there, then it's just, by early the next morning, okay? All right, now sometimes I may put a time, and you really want to, that's an absolute deadline, okay? I need to get these things, because I got to grade them, right? But, so just sometimes Tuesday or early Wednesday morning. I probably shouldn't say that, but okay. So we're still working on a damped, driven, simple harmonic oscillator, and we're not going to finish today. Okay, we're doing this really in depth, a lot of depth here. We want to now remember this is the total solution here. When you at time t is equal to 0, we switch on a drive. In this case, it's a cosine drive, a force with this amplitude, and it, looks like this in time. Right? It's a cosine. We've just arbitrarily chosen a cosine rather than a sine or anything else in between. And this is the solution. And there can be any initial conditions here. Incidentally, if you care, usually you don't care. Usually when people turn something on like this, they just turn it on and they wait until the transient dies. They're sure that the transient dies away, and we focus on the steady state. But to be complete here, we want to talk a little more about the transient, because it's something that you need to be aware of. For example, how long do you have to wait, right? So, all right, so this, as we said yesterday, this is actually the complete solution here for the displacement. And now let's, natural initial conditions here are, and these are practical too. Initially the oscillator is at rest, and initially it has no velocity, right? The mass is at rest at time t is equal to 0, and it has no velocity. It doesn't have to be this way. We've got our two independent constants here. We can fit this to any initial conditions. But let's just take these simple initial conditions here. Okay. We're also going to assume, to make it a little easier to deal with, we're going to assume weak damping. So the damping parameter is much less than omega naught. Now what does this mean here, much less? Does it mean this has to be a percent? Less than a percent? Less than 10%? That varies from, this is not real precise, this much less than. And I think we're going to be showing some graphs in the book. I think they chose, it's 10%. They chose 10%. Now they actually have the damped frequency here, but because beta is small, the damped frequency and the natural frequency are going to be very close. Okay, they chose a beta of 10% of this. Usually we don't think of that as small, but in this case it is small, because the effect of the dissipation here enters in as the square. Remember? Do I have here? So you'll see, for example, here's just one aspect of it, weak damping. Because this is squared here, and I've told you this before, with the beta 10% of this, because of the squares, it's going to become a 1% effect. And then when you take the square root, it's about 0.5%. So it's small, right? So when we make a statement like this, there's no universal reason, meaning behind how small this has to be. It has to be a percent. In this case, 10% is typically very good. Okay, so here's our full solution. We have to enforce the initial conditions on this. So at time t is equal to 0, this is 0, this is 0. The sine of negative theta will be minus the sine of theta. And so this is the position at time t is equal to 0, and we demand that equals 0. Here's the velocity at time t is equal to 0, and we demand that this is equal to 0. Now, the reason that KFCS chose small, weak damping here. Well, first of all, it's often the case in acoustics. It's often the case. This is small, as I've told you. But it makes the analysis easier if we do it here. So we're going to neglect, because we have a beta here, we're going to neglect this term compared to this term, or small beta. Now, to be consistent, when you do this, you see this omega d here? What should we do with that? If we're going to make this approximation here, what should we do there? To be consistent, we should set omega d equal to omega 0. We really should. Now, they don't do that, and I'm following them, okay? So it's their fault. No. But I just want you to be aware of this, that we're really not being consistent here. But it's not going to cause any trouble. Okay, we'll just stick with what they have. They have omega d here. And omega d will be very close, will be nearly the same as omega 0 for weak damping. Okay, so that's nice. We get rid of this term, and you can see what we have here. The first equation I can write like this. Just move this to the other side of the equation. I get this. And similarly, the second equation, we can move this to the other side and cancel the minus signs, and we get this. So we have two equations, and how many unknowns? Don't forget the unknowns, right? There are two unknowns, A and phi. That's what we have to determine here. So this happens a lot in oscillations and waves, dealing with the sinusoids here. And you can all solve two equations and two unknowns. Right? Now, these aren't linear equations into, there's trigonometric functions here. But the easiest way to do this is to recognize, and I don't know if we might have talked about this before. If I square each side of this equation and square each side of this equation, and then I add the left sides and add the right sides, what happens? Can you see that in your head? Yeah, we get the sine squared plus the cosine squared, which is always equal to 1. So we can quickly, easily eliminate phi from these two equations, and we can find out what A is. And all right, well, I did it out of order here. So what we just did there was square and add the two equations, and we get this. All right, oh, I can see why I did that, because there's more work to do here. How do we eliminate A? That's even easier, and I should have done that first. How do we eliminate A from these two equations? Take the ratio. Take this equation and put it underneath here. Divide the left-hand sides by each other and the right sides. That's still going to be an equality, because these are equalities. And the A cancels. Actually, we should do it this way so that we get the tangent. It's more common of a function, so we should go that way. And that tells us what phi is, what the tangent of phi is. It's equal to this. Now, what is this theta here? Remember, this is the definition of theta, and it's nice to think in terms, I find it useful to use this right triangle construction here, right? This is what we derived yesterday, I think. This is the phase angle of the complex impedance. This is the magnitude of the impedance. So this angle here, I can see from here that the tangent of theta is just going to be the mechanical resistance. The tangent of theta is going to be the reactance, the mechanical reactance, divided by the mechanical resistance, because the tangent is this divided by that. So we can eliminate that in terms of, quantities, fundamental parameters of our system. They're buried in here, right? This is a fundamental parameter, or closely related to it. Yeah, no, this is a fundamental parameter of our oscillation system, our oscillator here, because it's the dissipation factor. Because we're assuming a velocity resistance here, right? So that's fundamental. And this is the parameters are, we know what we can get this in terms of parameters of the oscillator. Okay, and here's the amplitude. Here's what we get when we do what I mentioned before. We get this expression. And now, again, we can eliminate the phase angle of the impedance, the complex impedance, again, from this diagram, and we get this. Now remember here, omega is the frequency of the drive, which can be anything. So make sure you don't confuse. This is very different. This is a parameter of the system here. right, or related to parameters of the system, of course, right? But this is a free parameter. What we have to play with is the amplitude of the force and the frequency of the force in our solution here. It can be anything. And that's the way we want it. We want to be able to explore what's going to happen when we sweep frequency. Right? Okay, at this point, I know it looks kind of complicated here, but now we've achieved a unique solution to the problem of switching on a drive at time t is equal to 0, where the oscillator is at rest in equilibrium. This is now, we've now nailed it completely down because we've found those two constants. So there's no freedom here. And this is unique. It's independent of the initial conditions, as I mentioned. We don't have any freedom. That's just, we know that. We know these quantities. So we've now nailed down these two. So now we have a unique solution to the problem. And it's interesting to plot it, and this is what KFCS does. So they'll be on the next, they're in the next page of the notes. I've scanned them. We're going to look at time. Oh, time series is going to be x as a function of time. This is a phrase that people, nonlinear people, usually use. So I have expertise in nonlinear dynamics. So I tend to use this, and the reason we use it is when you're looking at dynamical type systems and the motion is complicated, you want to have different windows. You want to have different views of what the motion is. You want to look at a fast Fourier transform, for example. You want to look at a time series. You want to look at a variable as a function of time. So distinguish and there are other views. There's Poincaré plots. Anybody ever studied chaos? Yeah. So it's all kinds of things we need to try to get different viewpoints and get a feeling for the motion. Sometimes one viewpoint, is better than another for what we're after. So time series is a common word to use for this, okay, and it's just x is a function of time. Well, it's not quite x, is it? Okay, well, we'll talk about that. So what they've got here, is, you see there's 3 different time series here. So what's being varied? Well, what's being varied is the drive frequency. So here, the drive frequency, I mentioned it here. Oh, it's probably in the caption. Well, I don't know if you guys can see that, but we're going to look at 3 different drive frequencies. 1/3 the damped frequency, which is very close to omega naught, right, the natural frequency. 1/3, 1, and 3. Okay? And in that order, here's what we get. Okay. Now you can see that the drive frequency is increasing as we go down. How can you see that? Well, eventually it's just going to be the steady state motion, right? The transient dies out. So you can see that over here, by roughly, somewhere around in here, very roughly, you're getting a pretty nice sinusoid here, right? And here, it's pretty, well, a little deviation there, but if they showed more of this, what you're going to find is these deviations here get smaller and smaller, and in the end, eventually, you have what looks to be a perfect sinusoid in all these cases. That's the steady state motion, right? Constant amplitude, constant frequency, constant phase shift, some kind of phase shift from the drive. Nothing's moving around there. So you can see here, the period is clearly getting less and less. It means the frequency is getting, right, when you look at the steady state motion here. Now you want to be real careful with all plots. You want to be careful. You always want to look at what the axes are. This is not just x. What is all this stuff here? I can't see it. But it's in the notes, it's in the book. What they've been forced to do, and they don't really tell you this, what they've been forced to do is, if they just used x here, okay, and normalized it to something that didn't involve the frequency of the drive is in this normalization, or this scaling here. Okay? If they didn't do that, does anybody know what's going to happen? Can you guess what's going to happen? This is being driven right? It's being driven at a frequency that's the transient frequency, the same. Omega equals omega d, right here. Well, the answer is one word, resonance, and we're going to spend a lot of time talking about that. We may start today and it'll go into next week. The amplitude, if they just plotted amplitude, this would be much bigger than these two things. And in fact, because we have weak damping, it could be anything. It could be a 10, factor of 10, could be 100, could be more. So in order, if they had the same scale here, and you clearly saw this case here, which is, as we'll see, is the resonance case. What's this going to look like? Well, you won't be able to see the structure. It'll just be like a straight line, approximately. And similarly, this, you won't be able to see it. So they've done that for clarity, but you always want to be careful, because this can be, if you don't recognize that, you could be misled, okay? So you want to notice that. There's something else here, and this is bad. So, okay, so here's the basic idea, right? There's a transient. And in the beginning, there's two terms in our solution. There's the steady state motion at the frequency of the drive, and then there's the transient at the damped frequency. Whenever you have more than one frequency, the motion looks complicated. I have seen this a lot. It's a little surprising, and you can see how this is complicated, right? Now why is this not so complicated? Do we have two frequencies? In general, you have two frequencies before the transient dies out. But what's special about this case? They're the same, okay? And now we get this nice growth. It's beautiful, what you'd expect. This is what you'd expect to see. But you only see it on resonance. And we'll define resonance, but when the drive frequency equals the damped frequency. And then here, oh, it looks complicated, okay? I mean, I've told people, I've done demonstrations of this, and I've sometimes say, well, doesn't that look chaotic? And yeah, you can actually think that it looks erratic and unpredictable, sensitive to initial conditions. It's not chaotic, it's just two frequencies. That's all it takes for it. The motion to look complicated. This, incidentally, you've all seen this before. Where is this? The book. Anybody have a copy of the book? I don't blame you if you didn't bring it. I don't bring it. Yeah, thank you, Sue. So you've all seen this, okay? Now, why did they do this? We usually don't care about this. We're just doing it now, just so you be aware of it, right? We usually only care about the steady state. So I don't know if it was KFCS or some graphics artist decided, the publisher decided we needed to have something look interesting. So it's a little, I've always sort of wondered why they did that, because it's really, it's not a main part of what this book is about. We're going to almost always focus on the steady state motion. Thanks. Okay, there's one more thing here, and they don't comment about this, or I didn't see it. What are the units of, this is going to be dimensionless units. See how they put one here? This has been normalized by something that involves a frequency. And it's been normalized such that the steady state motion has amplitude 1, no matter what the frequency is. That's what they've chosen here. What T, what is this? Is this a second? No, we don't. It's not going to be a second, right? You really need to put something dimensionless there, or you need to specify. What do you think those marks are? Well, I can take a guess, and so can you.
The time process.
Yes. Remember 1 over beta? Remember, the amplitude of the transient is decaying like this. So the characteristic time here is this 1 over beta. I don't know if we have a symbol. I don't know if we call it anything. Let me call it, maybe we call it tau. So this is also called the time constant. And you'll notice here, this could be 1 tau, this could be 2 tau. It's reasonable. You can show that once you hit 5 tau, you're essentially in you're very close to the steady state. Within less than 1%, I can't remember the number. But so I suspect that these marks here are, the time is in units of tau. So in other words, what they should have done, if they had done that, right? If they had done this, and you understand, they have to do, this is 1. Okay, etc. You need that too. then that nails it down. So I suspect that's what it is, but I'm not sure. Okay, any questions about that? So we'll get this. This is a very important special case here. We'll spend a lot of time talking about the resonance case. Because often in acoustics we want to we're going to drive things on resonance. It's a practical thing. Now there's another side to all this. When I switch on the drive, we get a transient. What if we switch off the drive? So this thing's in a steady state. Oops. Here, just look at this. What's going to happen if I switch off the drive? The system has damping in it, so it's going to decay, right? So that's a transient. That's transient motion. It's called a decay transient. What if you, and I've done this, I'm sure a lot of other people have too. What if you slowly turn down, you got a knob here for the drive amplitude. What if you slowly turn the drive amplitude to 0? Not quickly. Out here you're in the steady state and you relatively slowly turn the drive amplitude down to 0. What's the motion going to look like?
Does it continue to try to?
It's going to essentially be in the steady state, isn't it? It's just the amplitude is going to be in the steady state for a reduced amplitude, greater and greater reduction. So if you turn it sufficiently slowly, you'll actually be approximately in the steady state. So you can do that. Like I said, I've done it. Sometimes there are reasons for it to do it. But so there's really no transient, negligible transient. But let's go the other extreme. Let's assume we just switch it off, like we did over here. We switched it on, right? So let's assume we switch it off. There's going to be a transient. How's the system? What's the frequency of the system? The oscillator. The drive is gone. Omega D, right? Which is approximately omega 0 in our case. Okay, it's going to be going at the natural frequency or very close to it. There's no drive frequency now. We switched it off. Sometimes people want this decay transient. If you want an echo, it's kind of like an echo. Think of it as an echo. So sometimes that's wanted. You want some kind of echo for whatever reasons whatever you're doing here. Often you don't want it, you know. For example, a loudspeaker playing music or some audio signal. You want what's called faithful reproduction of the sound. Usually that's what you want. I'm sure there's cases where, but usually what you want is this signal, this electrical signal is coming in. And it's been recorded. Some music or whatever has been recorded, and you want the sound coming out here to faithfully reproduce that electrical signal. Right? Now, electrical signal involves changes in drive amplitude, changes in it could be a multitude of frequencies, right? It can be very much complicated, more complicated than what we've been dealing with. But the idea is there. The idea is that when the amplitude changes or something, if you get a transient, what is that going to mean for the sound out there? You aren't getting faithful reproduction. What'll tend to happen is it'll get kind of muddled, and it won't sound right. Right? So there are plenty of cases where you don't want these transients. So people go to effort to reduce them, but they're not perfect, as we'll see in the demonstration shortly. There's something else I have to say. Oh yeah, microphones is the same. How did you get the electrical signal from the music? How did that ever happen in the first place? Well, usually you've used one or more microphones to record some music. You want those microphones to respond faithfully to the sound, to the acoustical signal coming in. If there are transients there, you're not faithfully recording the signal. So it works both ends. Okay, so here's a demo, and I've improved it a lot from the past. And I'm not going to tell you how much time I spent on this because you wouldn't believe me anyway. So here's the idea. To exhibit a transient. A loudspeaker, we will talk, next quarter we'll talk about how loudspeakers work. Most of you may know it's very simple. A conventional loudspeaker is actually quite simple. And then in the transducers course is a lot more detail, of course. But the idea is that there's a cone, right, for a standard conventional loudspeaker, a cone that's oscillating like this, and it creates alternately compressions and expansions of the air, right? And those compressions and expansions, that's sound, and it propagates out. So you go, if I'm going like this with this, I'm sending out a sound wave here of compressions and expansions. It travels at the speed of sound. Well, how does it move? Well, at the base here, there's a coil, a circular coil of wire. It's called the voice coil. It's an old name, and it sits in a magnetic gap. So there, if I start diagramming this, we'll spend too much time on it. So this is just brief right now. Right? There's actually a radial magnetic field here. So this voice coil sits in this magnetic gap here, and the magnetic field lines go like that. When you put a current through the voice coil, what's going to happen? You have a current and a magnetic field, there'll be a force, one way or the other. If the current is oscillating, there'll be an oscillatory force. So that's it. I mean, that's about it for a conventional loudspeaker. And we'll go into more detail later in the sequence. But you can see that, one more thing I got to tell you. This cone is just not free here. There's what's called a surround here that anchors it to the frame. So when this goes up like this, there's a restoring force due to the surround. There's also, you got to keep the voice coil centered in the magnetic gap, or it'll rub. So there's what's called a spider, and it's universally brown. I don't know why that is, okay? But maybe you've seen it. It looks kind of like this. It's this corrugated type thing. When the cone moves up and the voice coil moves up, that also supplies some restoring force. So we have a restoring force, you know, that approximately obeys Hooke's law over some range of amplitudes. We've got inertia, right? The mass here, the moving mass, including the voice coil. This is a mass on a spring. This is like a mass on a spring. And we've got a drive. We drive it with the magnetic force. There's another source of inertia. What's that? And this is where it gets complicated. We'll spend time next quarter doing this. The air. This is not in a vacuum. I mean, you could operate a loudspeaker in a vacuum if you wanted to. But the air supplies inertia and damping too. And calculating that is a big part of the next course. It gets a little complicated. Okay, so what we're going to do here is not apply a sinusoidal signal across. To exhibit the transient, we're going to apply a square wave, which is easy to do with a function generator. Here's function, I can't really, trust me, this is a function generator. And I've got it set for a square wave here. And it's better to do, I'm going to do it at 2 hertz. Okay, so you can see here, this is half a cycle. This is a cycle. No, what am I saying there? A cycle is from like here to here. So, this is wrong. Don't worry about it. I'll correct it. So this is at 2 hertz. That's 2 cycles per second, right? So 1 cycle, which is from here to here, is going to be half a second. Okay, so this is not right. Yeah. So what's the whole idea? Why am I doing this? Well, we can model this. This gets a little complicated, but we can capture the basic physics by thinking of a mechanical oscillator. When I have this constant voltage here in some direction, I'm going to get approximately a constant current. That's where it gets a little complicated, and I've never gone through the analysis, but I think it's a small effect. We have essentially a constant current. When I have a constant current through here, there's a constant magnetic force. The equilibrium position will be shifted. It's just like if you have a mass on a spring and I exert a constant force, the equilibrium moves over there. But then, half a cycle later, the equilibrium position is shifted to the other side, right? So a natural mechanical model for this is we have our mass on a spring, and what we're doing is we're moving this quickly, relatively quickly. This really doesn't have time to respond. We're moving it there, then there, then there, then there. So when we move it like this, let's say it's at rest here and we just turn it on, this goes over here. This thing is going to, has to decay down to its new equilibrium position. So that's the transient. All right, so let's see what it looks like. And then half a cycle later, it's going to, when the equilibrium point's over here, it's going to have to go here and it's going to ring down over here. So we expect something that looks like this for the displacement of the cone. Now, how do we measure that, the displacement of the cone? There are ways of doing that, but the easiest thing to do is just, this is producing sound, so we put a microphone there. So it's not actually a direct measurement, and it's not going to look like this. When the loudspeaker goes like that, it creates a compression, and then there's this expansion here. When it does this, there'll be a compression, and we expect it to ring down. So it'll be generating a little bit of a sound wave here. We won't see this because we're just picking up on the sound wave. We're not measuring the actual displacement. So let's do this. Oh, here's the microphone. Okay, and sorry. Oh. Oh, okay. Okay, so this is an oscilloscope. This is coming from here. You can see it on 10 here. This is time. This is the voltage from the microphone. It's basically proportional to the sound pressure. And this is real time. Well, it's a little bit of a lag. It has to take a time series, a time record, and then it puts it up here. So you can see, we can just focus on this. Here's what the sound pressure is doing, or you can think of it as the displacement, approximately. It spikes out here. It turns around, goes down here, goes up there, and then what does it do? It gets lost in the noise, right? And noise is, down around here we've got noise problems. But I spent a lot of time optimizing. It's better than when I started, okay? Part of the noise, incidentally, is coming from the fans in this equipment here, especially the scope. That's if I could turn off the scope and still get a trace, you'll see that this would be smaller. We can't do that, okay? Oops. I touched the keyboard. Did I do anything? Oh, shit. Okay, I think it's okay. My voice is also noise in there. So the first thing I want to look at here is, so we see this, we do see the ring down. You see the transient response as we expected. Now, why is this alternating here? Why is this? You can see this is the maximum. So remember, we have this.
Which way you're.
Right. So when the cone is going this way, and a compression is being created. So that's be like positive pressure compared to the equilibrium pressure. When it goes this way, what happens? It's an expansion, it's negative pressure. So it's doing exactly what it should do. Yeah, we expect that. Now we can, finally we can zoom in here a little bit. I'm going to zoom in time. Yeah, so here, now what the oscilloscope has decided to do is to we're triggering on successive ones. So you can see that there's a compression, expansion, okay? And now you can see the decay a little bit better here. It's a pretty quick decay, right? And that's part of the reason, these loudspeakers, actually in principle, is a very simple thing. And, but you can pay. Actually, they're not that expensive. You might think they're that expensive, but they're really not that expensive. But part of what you're paying for is you really don't want this. You don't want this. And you can see it's been minimized. It's been made small. You don't want this thing to sit there and just ring down. You're not going to get the faithful reproduction of sound. Okay, any questions?
I was curious, are those modeled by like Dirac delta functions? Those do they have anything to do with this? Or no?
I don't teach Dirac delta functions here, okay? They're a limiting case of a spike where it goes to infinite amplitude. A Dirac delta function is a curve that where you have a peak like this, and this goes to infinity, and the characteristic width here goes to 0. Okay? Now, if you want to know what those things look like, we did it. We did it. Here's the math. Yeah. This should, if you want to quantitatively explore this, we have in this case we have a theory. Sometimes when you do experiments or demonstrations, you don't have a theory. Now we do have to make the connection. This is displacement, and we measured pressure, so we have to make the connection between the displacement and the sound field. But that can be done. Okay, and that's really part of next course. Okay, any other questions or comments? It's a nice demo, I think. Okay, so power, energy, power. Power is energy per unit time or work per unit time, same thing. And it's almost always important in physics. Just because we want to know where's the energy going, it's usually not important because we're worried about wasting energy or an issue like that. But it's more fundamental. We just want to know what the energy balance is, and it's ultimately going to be useful because typically you want acoustic devices to be efficient, and efficiency is really not wasting energy. That's what we're talking about. So let's look at specifically the power here. So work per unit time, or energy per unit time. Work is force times, this is kind of semi-rigorous. Work is force times displacement, right? From mechanics. And now I can choose to put the time underneath the displacement, and that's the velocity. So you can see that the power is the force times the velocity. So we have our oscillator. We're back to our, here we are, which we used as a model for that. And there's some external force here exerted on the mass M, stiffness S, and there's some damping. We have some, we can put it in as a dash plot. We have some damping here. So when this has some instantaneous velocity, this is some instantaneous force. When they're pointing in the same direction, I'm putting energy into the oscillator. But sometimes it's going to be the opposite way. What happens there? What happens what's the power there? It's negative. Energy from the system is going into the driving mechanism. So in general, you want to recognize here that energy is going into and out of the system. So the power is the product. To get the force, this is the real part of the complex force. I put it here. Here is the velocity, which is the real part of the complex velocity. And by the way, you need to take the real parts before you multiply them. If you just multiply the complex force times the complex velocity, you will have made a mistake. Because remember we did a homework problem. You can't commute these operations. Taking the product and the real part, we have to do this, because this is the proper thing. It's not the same as the real part of the product of the complex numbers. So you got to do it this way. Now, almost always what we're interested in here is the average power. The power, this is the instantaneous power, and that's what that I stands for. And the reason KFCS did this is we're going to go to the average power without an I, and then we're not going to use this anymore. Okay, so that's why they did it. The average power is the time average, and you only need, because we're looking at steady state motion here, which I should have mentioned. Yeah, here it is in the notes. We're looking at steady state motion. We just need to average over one cycle of the drive or the response. Just one cycle, because this is steady state motion. Okay, so let's integrate. In this case, the average, we need to integrate and then divide by the period. So we're integrating over one cycle, the instantaneous power, dividing by the period. This is going to be our average power. And that's almost always what people are interested in, what's relevant. All right, so we can substitute in. Here's the, I've substituted this expression into here, taken the constants outside, and so here's the integral that we need to analyze here. It's a cosine of omega t and also a cosine omega t, but there's a phase shift. And now you're going to start to appreciate why phase shifts are so important. It'll dramatically come out of this analysis here. It makes a big difference with this angles. And some of you have probably seen this before, maybe with transformers, electrical, or I don't know, doesn't matter. So it's critical what that is. So how do we analyze this? Well, the easiest thing to do is just recognize the trigonometric identity. The cosine of a sum or difference of two angles is the product of the cosines and the product of the sines, right? This is just a trigonometric identity. I don't know if we've probably seen it before in this, I don't know. But anyway, it's a standard high school trigonometric identity. Now you want to notice here that we're integrating over time. This theta is constant. It's just the constant phase angle of the, the impedance. Remember, it's capital theta. So these factors right here we get the integral becomes two integrals. These factors right here come outside. So what we're left with is, for the first integral, we're left with just cosine squared of omega t. So what's the average value of the cosine squared of omega t? I think we did this in mechanics, right? Here's what the cosine squared, this is the cosine squared. It's a sinusoid. And how do I know that? Well, I know it because of this identity, this double angle formula, or whatever we're going to call it. This is another trigonometric identity. This tells me, this is actually the Fourier expansion, Fourier representation of this. A cosine squared consists of a DC term and then a nice oscillatory term at twice the frequency of this. So it looks like this, right? Now, this is easy. I want to emphasize this because you don't want to have to go through this this integration. It's really actually obvious. Once you recognize that the cosine squared of omega t looks like that, what's the average value of that curve right there? It spends just the same amount of time up there as it does down there. There's a symmetry about this 1/2 line here. So the average value is going to be 1/2. The average value of the square of a sinusoid, cosine, sine, or any phase in between. Phase is not relevant. It's going to be the same for the sine, of course, right? The phase is not important here. Is 1/2. What about the other term? Here we hit cosine times sine. All right? Now you can think about this, and you can draw some curves, or you can use a trigonometric identity, which is quicker. I'll use that. What this is the sine of 2 omega t with a factor of 1/2. This is another trigonometric identity. And most people think of this as we use the cosine of the sum or difference of two angles. There's a similar identity for the sine of the sum or difference. And in this case, both of those terms are the same, and we just get this. So it's related to that previous identity. What's the average value of this? Obviously 0, right? So after a while, you don't have to go through this. You'll be able to see this in your head, and it makes life easier. Because we use this a fair amount of time. Okay, so here's what we get. this is not this is 0. We get the average value of the cosine squared, which is 1/2, and we get this, and this is part of the average. And don't forget, we have a cosine of theta there. So what we get for the average power is this. And I was when I looked at this last night, I was thinking, why didn't I put a box? This has got to be important. Well, we can beat this down, make this simpler. That's why there's no box there. We can make it simpler. First of all, remember theta. Remember our right triangle. Here it is. Use this a lot. Here's the magnitude of the impedance. We're in the complex plane here, if you like. This is the real part of the impedance and the imaginary part, the resistance and the reactance. So I need the cosine of theta here. Well, I can see that the cosine theta is going to be the resistance divided by the magnitude of the impedance. So I get this. All right? Now, this is an important formula, and we will use it, but we can make it even easier. That's why I didn't put a box around there. Okay? We can make this so that you can't forget it, believe it or not. I know you think I'm crazy. How can you know, I can't remember. I don't like this because I can't remember that. But where we're headed is we're going to be able to remember it. Okay? Now, I've got some additional things here. Yeah?
Sir, just where we lost sine theta for 24.
Pardon me?
Previous page, please. The cosine theta is coming from that formula, yes, right? And we lost sine theta in somewhere.
Mm-hmm. Because of the averaging, it averages to 0. Right. So this is gone,
Yeah.
because the cosine times the sine averaged to 0. And again, you can think about that. You don't have to go through the math. If you just think about it, cosine, you can be led to the fact that it's going to be above the origin the same amount of time it is below 0 here. So it averages to 0. Okay. So let me see here. Okay, now you'll notice here, the instantaneous power can be going in and can be going out. On the average, though, what is this? This is a positive number, right? So it's actually equal to or greater than 0. And when I type these notes, which I will do someday, I'm going to fix this here. So that makes sense because, and where's the energy going? Oh, this is a good question. Where is that energy going? Anybody? Is it changing the energy of the oscillator? No, why? We're in the steady state. What does steady state mean? Constant amplitude, constant, frequency. So the energy of the oscillator itself, the kinetic energy plus the potential energy in the spring, that's constant. So where is this energy going? It's the dissipation, whatever the damping mechanism is. It's appearing as heat. That energy is ultimately, it's going to appear as heat. Okay. Now you'll notice something interesting here, and this happens in transformers, if there's any of you aware of this. Theta can be 90 degrees. If we have no mechanical resistance, then what's the cosine of theta? Well, there it is. It's 0. And that's actually a check on our solution, because if I'm driving this, what has to be the average energy input in the steady state? There's no choice. There can't be any energy, net energy going in, because where would it go? We don't have a source of dissipation. And we have steady state motion. So that's actually a check on the solution. The fact that when the mechanical, theta is equal to 90 degrees, which means no mechanical resistance, this has to be 0, because there's no place for that energy to go. So steady state motion and no damping. So that's a check. Okay, now we're supposed to go here. So here's the boxed expression that you've been anxiously waiting for. And I can tell you, you forgot, but that's okay. Let me just pretend. We can make an interesting step here. Remember this? This is really sort of the usefulness of the impedance. we take the complex impedance, being the ratio of the complex drive divided by the complex response, take the magnitude, and this tells us what the velocity amplitude is. We've seen it before, it's simple. I can use this and substitute it into here. And you'll notice this is squared and this is squared, and we get this. Now, I can remember this, and so can you, because we're back to where we started from when we started to get into the impedance. We're back to a resistor. If I have a resistor, what's the power rate of energy loss, or heating in the resistor? I squared R, right? Everybody knows this. So that's for in the electrical case. It's I squared times the electrical, where this is the current, right? Now, some of you, I don't know if you remember this, but that's true for RMS, for the root mean square, not for the peak value. We're using peak values here. We have amplitudes. This is the peak. The velocity here is oscillating. This is the peak. So when you use peak values, you need to put a 1/2 here. So for a resistor, this is the power that you're losing in a resistor. And there is an analogy, as we will discuss later, between acoustics, between oscillators like this and electrical circuits, mechanical circuits and electrical circuits. And it won't surprise you when I tell you that what's analogous to the current here is the velocity. Velocity and current are analogous. So, all you have to do for the power dissipated in an oscillator in steady state is think of a resistor, 1/2 I squared R, convert the electrical quantities to the analogous mechanical quantities. So we go from I to U and electrical resistance to mechanical resistance, and we get that. So this is easy to remember. And I know it may seem a little complicated to you because you got to remember that, but after a while, this is what I use. We don't have to worry about this. We can retrieve any of these this expression from here if we use this. So these are two things that are easy to remember, but it's hard to remember.
Sorry, sir, where does the 1/2 come from again?
Yeah, we're actually going to talk about this in more depth. There are different kinds of amplitudes. Whenever you have an oscillatory something, there's different types of amplitudes. So just real quickly, here's a wave. And you can think of this in space or time. It doesn't really matter. This amplitude, this is called the peak amplitude. What's this called? It's actually 2A. That's called the peak to peak. They call that that's what they call it. I guess it's peak to crest, or trough to crest here. So some people use this as an amplitude. Then there's the root mean square amplitude. The root mean square is down by the square root of 2, which is, and you can see why people would use the root mean square. It gets rid of the half. If you use the root mean square current here. So then you're just going to get that. So that's one of the reasons the root mean square is popular. But in this course, we're almost always going to use peak amplitudes. So, and we'll see this later. Incidentally, who uses this? Remember, this is the Naval Postgraduate School, right?
Oceanography.
Yeah, ocean waves. When you're estimating the waves of the ocean, wave height, it's natural to look, I think this is one of the reasons they do it, it's natural to look at peak-to-peak amplitudes rather than peak. So you just need to recognize that, they're different. There's 3 different ways of measuring amplitude. So, okay, any other questions? Okay.